Let me just do a quick check to make sure that this is actually streaming. Quick check to make sure that this. Okay, it is streaming. All right. Beautiful mind here. And so we're continuing our discussion of calculus. Let's look at it. One on differentiation, and we're going to be looking at section 1.4 differentiation using limits of different quotients. So in the last section, we explored this concept of a difference quotient. And again, difference quotient, all it is just the slope between 2 points. X1 is just X and X2 is X plus H, right? So we're creating some small change in a horizontal change in X, right? And we consider the corresponding Y. And again, difference quotient is just the slope between the 2 points. So now we want to introduce this notion or concept or idea of differentiation using limits of difference quotient, right? So we, towards the end of the last section, we were seeing how the slope was affected as that second point got closer and closer to the first point, right? So that H was, again, just some small change in X. So now we want to see, well, let's take a limit as H tends to 0. As H gets closer and closer to 0, what is this slope telling us or giving us a sense of, right? Okay. So some objectives here, we like to find derivatives and values of derivatives. And we like to find equations of tangent lines, right? Remember in the previous section, we were exploring slope of secant lines. Secant lines are lines that intersect curves at more than 1 point. And so let's see what we mean by a tangent line. So the slope of a tangent line at some point x comma f of x is going to be, the slope is going to be the limit as h tends to 0 of the difference quotient, right? So for instance, say we had some p and a q, and it was just x plus h, right? So then as that h gets smaller and smaller and smaller, this second point gets closer and closer and closer to our first point, right? So as long as h is greater than 0, we're talking about a tangent line. But as that second point, as h tends to 0, and that second point gets closer and closer to the first, we get a better and better approximation of the slope of a tangent line. So this is a tangent line. A tangent line is a line that intersects a curve at one point in this fashion. It doesn't cross a curve like that. It grazes the curve like that, right? So that's what we mean by a tangent line. Versus a secant line is going to cross a curve at more than 1 point, right? So we're using the slope of the secant line, and we're considering several slopes as that second point is closer and closer to the first, we get a better and better approximation to the slope of the tangent line, right? Because if we just try to take the slope of the tangent line by itself, that's a tangent line, but because it's like so close, you can easily miss it. If you just try to eyeball it or like just try to do it like that, it's very easy to like get the wrong slope, right, of the tangent line. So we use the slope of a secant line, and we take the limit as that change in x goes to 0. In other words, as h goes to 0, to get a better and better approximation for the slope of the tangent line at a point, right? Is also the instantaneous rate of change of f at x, right? Tangent line is basically the limit as h tends to 0 of the difference quotient. Y equals f of x is derivative of x at x is the function f prime defined by, again, so we're defining the derivative of a function is the limit as h tends to 0 of the difference quotient, right? So again, long story short, the derivative is the slope of a tangent line function. So again, f prime is the limit as h tends to 0 of the difference quotient, provided the limit exists. If f prime exists, then we say that f is differentiable at x. F of x equal to x squared, find f prime of x, then find f prime of -3 and f prime of 4. All All right. Okay. So for f prime, again, all f prime is the limit as h tends to 0. Now, again, this is the longer version. Just do the best you can with this. I want to say in the next section, we're going to start introducing shortcuts. Like what you're going to see in this section, it might take like a good amount of space and a little bit of brain processing power. But then when you get to the next section, all the stuff we're doing here, we can do it in like an instant. We can look at the thing, look at the function, and actually just jump straight to the answer. So we have all these shortcuts for jumping straight to the answer. And to me, it's fun, but let's get to this as best we can, right? So we have this f of x. So now we just said, let's go here, that f prime as h tends to 0 of f of x plus h minus f of x over h, right? The limit is h tend to 0 of the difference quotient. And f prime, okay? So let's keep going. So this is going to be the limit as h tends to 0. Now we need to plug in x plus h into f of x. So if you plug it in and expand it, you'll get x squared plus 2xh plus h squared minus x squared over h, right? Like terms and simplify, this guy is canceled by this. We could go ahead, let's just go ahead and factor out our h's from the remaining terms. So this h is going to cancel this one and this one, right? We have the limit as h tends to 0. That's all that remains, right? When we did our discussion on limits, at this point, we can actually just plug in h is 0. So as h tends to 0, that this second term here essentially goes to 0. And what we're left with is 2x, right? So we're saying that f prime is 2x. Yeah, that's fine. So then we're asked to find f prime of -3 and f prime of 4. So basically what this is going to be the slope of the tangent line when x is -3. And this is going to be, f prime of 4 is going to be the slope of the tangent line when x is 4. F prime of -3 is 2 times -3, which is -6. So it should have the slope of -6. And f prime of 4 times 4, which is 8. Okay. Well, these are telling us the slope of the tangent line at these different x values, right? Let's keep going. So f prime is going to be the limit as h tends to 0 of the difference quotient. So then they got this, and if you expand it, you see it here where they cancel. You factor out your h's, and then they cancel here. And then we got to this point, and then you take the limit as h tends to 0. Again, this guy goes to 0, and we finish here for the f prime of x equals 2x, and then I think we got these results. Okay. Was this find f prime of x, then find, so it's a repeat just with the difference quotient. I'm gonna do this with the difference quotient, okay. So again, we said the f prime of x equals the limit as h tends to 0 of f of x plus h minus f of x over h, okay? Quickly, let's make sure we're still moving. Okay, let's keep going. Okay. So now x plus h, we're plugging it into x cubed. Let's see if I can jump straight to the result here. So this one should be x cubed 3x squared h plus 3xh squared plus h cubed. So I'm just kind of piggybacking off what we did in section 1.3 with the similar when we expanded x plus h squared, right? I'm just kind of pulling from there. So then, and actually, we still need our limit as h tends to 0. Let me do this is canceled by this. Notice that the remaining terms all have h. You can go ahead. We probably should write another line. I'm just going to go ahead and do it for the sake of time and space. This turns this into a 2. This is gone, this is gone, and this is gone, right? Now let's see if we can capture what's remaining. So then this is going to be equal to the limit as h tends to 0 of, let's see, that first term we have is 3x squared plus 3xh. So now I think once we cancel the h's like that, we're ready to essentially just evaluate when h is 0, or to evaluate the limit when h as h tends to 0. So then what happens, we're simply just plugging. That goes to 0, this goes to 0. And we're left with 3x squared. So we're saying the f prime of x is 3x squared. Again, we have a shortcut. You can bypass all of the difference quotient stuff. I don't even mind if you bypass it in this, but if you know the shortcut, you can use it. We'll talk about it in the upcoming section. So then we're asked to find f prime of 1. That's going to be basically 3 times 1 squared, which is 3. And then we're asked to find f prime of 1.5. Nope. To find f prime of -1. So it's going to be 3 times -1 squared. And then we're asked to find f prime of 1.5. I want to say 15 squared is 225. So 225, so this should be 2.25. 3, 2.25. 6.75. So again, what these numbers are telling us are the slope. Let me see. If you think about the original function, it should be the slope of the tangent line at these different x values. Three, and we got 6.75. Let's see, how do we do? So you see 3x squared, 3 and 6.75. So then use the results from example 1 and 2 to find the derivative of this, and then calculate f prime of -2 and f prime of 4. Now, since we already found the derivative of each of those, then we can actually just in this context, we can just add those derivatives together, right? So then what we can do, we can use the results that we are, instead of calculating those difference quotient again, we can just use the results. So then f prime of x should be 3x squared plus 2x, right? So then f prime of not 2, but negative 2 is 3. And again, the x in this case is negative 2. So that's 4 times 3 is 12. Or 3 times x squared plus 2 times x. Again, x in this case is 4. 16 times 3 30 plus 48. These are the slope of the tangent lines at these points. That 6. So use the results from example 1 and 2 to find the derivative. From example 1, we know the derivative of x squared was 2x. From example 2, we know the derivative of x cubed was 3x squared. So using the limit property 3, we know that f prime is going to be this plus this, right? That's what we did. So then f prime is negative 2, 8, and 56. I think we got. These results mean that when x is negative 2, the slope of the tangent line is 8. And when x is 4, the slope of the tangent line is 56. Basically this, find the derivative, find f prime of 2, find an equation of the tangent line. Okay, do I need space? We're still using limit of the difference quotient. I think I can get it to fit. Let's try to get it to fit. So f prime of x is going to be the limit as h tends to 0. Now, if we plug in x plus h, so that's going to be x plus h over 3 minus 3 over x all over h. It's going to be equal to the limit as h tends to 0. Let's say a common denominator. We can multiply what top and bottom by x. And then here. First we get x, 2x, and 8. H. But instead of putting all over h, when you multiply by the reciprocal, essentially the h ends up here. So then this cancels this h is canceled by this h. And that's going to be, why don't we have x, we still have the limit as h tends to 0. Now bottom we have x times x plus h. On top we have negative 3. Now because we were able to successfully cancel the h's here and here, now we can pass the limit as h tends to 0, because if this h was still there, then we would get 0 over 0. Or we get, yeah, we get 0 over 0. Which is like, we can't use that. So once we were able to cancel these h's, now we can take the limit as h tends to 0. So then once we take the limit as h tends to 0, basically this term goes to 0. Looks like we are left with negative 3 over x squared. So then f prime of 2 is going to be 2 squared under negative 3. So then negative 4. Here in the southeast, we got city shut down. Like, just we're not there was a lot of ice and snow and stuff like that. Find an equation of the tangent line. So again, this -3/4 is telling us the slope of the tangent line. So we have the slope, and we can find a point. When x is 2, we can find the point on the graph. We have a slope and a point. We can find the equation of the line, right? So when x is 2, in the original, the corresponding y is what 3 right here. Okay. So we're going to use y equals mx plus b really quickly. We need to find, we got the slope, we need the y-intercept. So when x is 2, y is 3/2. So we're going to say 3/2 3/4. X is 2. The only thing we don't know is our y-intercept. 3/2. Because again, so you got a 2 on top and a 4 on bottom. So that becomes 3/2. So move this to the other side. We add 3/2 to both sides. So then 3/2 plus 3/2 should be what? 6? 6/2. So 6 divided by 2 is 3, right? So then the equation of the tangent line should be y equals 3/4x. That should be the equation of the tangent line when x is 2. And we can confirm all this by like graphing. Like if we graph the curve, we graph the function 3/x, and we graph this -3/4 x plus 3 on the same plane, this should intersect that curve as a tangent line. Let's see. Let's see, how do we do? What time is it? It is 4:45 in the morning. Okay. So let's see. F prime, the limit is h tends to 0, blah, 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 blah. You see this -3/x squared. I think that's what we got. But then f prime of 2 was a -3/4. So then when x is 2, our slope was a -3/4, and the corresponding y value was a +3. 3, right? We got our y-intercept was 3. So then we got a -3/4x plus 3 is the equation of the tangent line. Okay. So repeat example 3a for f of x equals a -2/x. What are the similarities in the method? I think I'm going to rely on my type because I'm about to fall asleep. I'm tired. Repeat example 3a. So f of x equals a -2/x. What are the similarities? So we got this -2/x plus h minus a -2/x. You can do a double negative positive common denominator right here. Notice these guys cancel. This h is going to cancel this h, right? And then here, and then if we take the limit as h tends to 0, we're going to get this 2/x squared. Where a function is not differentiable, a function f of x is not differentiable at a point x equals a if there's a corner, right? So if a function has a sharp edge or corner, then we can't differentiate because again, we can't find the slope of the tangent line. Because if we try to, there's like too many tangent lines. We can do one like this. That's a tangent line. That's a tangent line. That's a tangent line. There's like infinite number, right? So that's why we can't do it. You can't differentiate at a sharp corner. So a function that is not differentiable at a point if there's a corner, right? So here's a corner, here's a corner, here are corners. Those points. Yeah, see, this is what I skip because I know like when I get sleepy, I start like repeating myself and all this other stuff, but it's okay. This is gonna come up soon too, but it's okay. Here's another example where a function is not differentiable. A function f of x is not differentiable at a point x equals a if there's a vertical tangent at a. All right, so if we try to draw a vertical line at this point, it creates a vertical tangent line. So we say it's not differentiable. It doesn't have a vertical. That's like undefined. A function is not different. A function f of x is not differentiable at a point x equals a if it's not continuous at a. Right. So we got this huge gap. You know, we start tracing from the left. We have to pick the pen up, and you know, because we have to pick the pen up, there's a gap. So it's not differentiable when x is -2, because the function is not. So where is this not differentiable? Basically at the vertex, right? So if we think about the absolute value function, normally the vertex is at the origin. We subtracted 6 inside our function, so that's going to move the vertex to the right by 6 units. So the corner should be at the point 6, 0. So where is this not differentiable? At the point 6, 0. Basically where the vertex is. I think we're almost done. We don't have a, oh, no, we are done. Okay. So differentiation using limits of difference quotients, a quick summary. A tangent line is a line that touches a smooth curve at a single point. It's called the point of tangency. Okay. The derivative of a function is defined by, so f prime of x, which is the derivative, is going to be the limit as, that should be as h. So that's going to be the limit as h tends to 0 of basically the difference quotient. The slope of the tangent line, the slope of the tangent line to the graph of y, there should be some space in there, at x equals a is the value of the derivative at x equals a. That is the slope of the tangent line at x equals a is f prime of a. The slope of tangent lines are interpreted as instantaneous rates of change, right? Because again, to talk about slope, we generally need 2 points. So if we're working at a tangent line, we only have 1 point. So that's why you have this like nomenclature of like instantaneous rates of change. And we use like the limit is h tends to 0. We use the limit definition of the difference quotient to get the best approximation of the slope of the tangent line at a point. The equation of a tangent line x equals a is found by simplifying. Okay. Or x minus a. Oh, the equation. All right, so that's the point slope form. Because you have your slope, right? And then basically y minus y1 equals m times x minus x1. That's the point slope form. So when you want the equation of the tangent line, you can use this formula. We took the slope. I use the slope intercept form, y equals mx plus b, and then solve for the b. But it's the same thing. This is just use a point slope form. If a function is differentiable at a point x equals a, then it is continuous at x equals a. That is, differentiability implies continuity. But the reverse is not necessarily true. Continuity does not imply differentiability, but differentiability implies that it's continuous. It has to be continuous. And then, however, continuity at a point does not imply differentiability. A good example is the absolute value function. The absolute value function is continuous everywhere, but it's not differentiable everywhere. Or any function whose graph has a corner. Continuity alone is not sufficient to guarantee differentiability. A function is not differentiable at a point x equals a if there's basically a hole or a gap. It's called that a discontinuity. If there's a corner at x equals a, or if there's a vertical tangent at x equals a. Okay. fun. That was much more smooth than my last one. Okay. So we'll continue this discussion. Hopefully this is okay. And I'll try to give, I don't want to give too much work. I just want you to try, I just want to expose this stuff to you and get you started because we got a lot of stuff we got to get through. Okay. So on that note, we're going to end the session here. And for one beautiful mind to another, enjoy the rest of your day. Okay. Take care. Peace.